So welcome everybody. Why don't we give folks a couple minutes while people are transferring in from other sessions, and we will get started shortly. This is Program Analysis 3. All right, it looks like we're kind of leveling off here. So welcome to Program Analysis 3. My name is Travis Bro. I am your session chair. We have 5 really great papers lined up for presentation today. We'll be following the standard protocol, which is 5 minutes per presenter, and then we will use the summary remaining time for questions to all presenters. So hopefully folks have brought their questions. If not, hopefully these 5-minute presentations really stimulate our thinking and invite us to ask questions. The plan is to go in order, and so the first talk will be by Toufiq Ahmed, and this is a paper titled Learning to Find Usages of Library Functions in Optimized Binaries. Toufiq, take it away.
Thank you. Thank you so much. So let me share my screen. Okay. Can you see my screen?
We can.
Okay, thank you. So today I'm going to discuss about our recent TSC paper, Learning to Find Usages of Library Functions in Optimized Binaries. I'm Toufiq. I'm a 4th-year PhD candidate from UC Davis. This work was done by me, my advisor, Professor Prem Kumar Devanbu, and Ananda Shaksam. So library function usage is often hard to find in optimized binaries. Optimization transforms a natural code into something that is entirely unrecognizable. Understanding the binary's behavior or reverse engineering is a very time-consuming task, but a very useful one. Binaries can be harmful or guilty of intellectual property theft. On top of that, this optimization makes this reverse engineering task difficult by making the function call inline. So let's look into this example here. There are 2 code snippets in the screen. On the left, we have a function that is written in C. And on the right, we have the decompiled version of that C function. You can see that there are 4 function calls in the original source code, but the decompiler Ghidra fails to recover all of them. So the one function called string copy is missing here. So in this paper, we propose a deep learning based approach that will recover this missing string copy function for the reverse engineer and help them understand the behavior of the binaries. So to fulfill this goal, we propose an automatic labeling scheme to generate dataset of binaries labeled with the actual function usages. And we also presented that our paper Funkry combined with Ghidra achieves state-of-the-art performance in function recovery call task. So let's look into a pipeline, how this decompilation thing works and why Funkry can help us. So the complete pipeline starts with the source code. The compiler compiles the program and do some optimization and give us the binaries. And these binaries are the real world starting point for the reverse engineer. The reverse engineer take these binaries and use some state-of-the-art tools like Ghidra, IDA Pro, and produce assembly and decompiled code from them. And they try to find the meaning of this code from this decompiled and assembly version. And here, Funkry can work on top of this decompiled version and find the missing functions for us, like string copy in the example. Building C projects is a bit difficult because of the dependencies. So we follow Bugswarm that came in 2019 for building this project. But there is some differences between the objective of Bugswarm and our project. Bugswarm did not support C, so we had to build a lot of C projects. So we modified this Bugswarm and we built our own tools, Beanswarm. And there are several steps that Bugswarm does for us. It can identify the right Docker container that a project uses. You can download the projects into the container, install the dependencies. That's the most difficult part for building a C project. And you can build the project using its script and the Travis configuration of the project. So after building this project using Beanswarm, we can decompile these binaries and have some decompiled versions of those source code. So now we have two versions. One is the source code and one is the decompiled code, like on the left, something like looks like or in the left side of this snippet. So now we have two versions like the source code and decompiled version. We can compare those two source code and find which functions are missing there. After finding those missing functions, we can insert some indelible markers into the source code and build the project and decompile the project again. And after that decompilation, we can have something that I'm presenting on the right side of the screen, like this, the decompiled version of the same source code with one message inserted, like a memset function is inlined here. So using this data on the right side, we can generate a data set for the deep learning based model and for the deep learning based model, and we can train a model with this kind of data. So we have tried several approaches for inserting the indelible markers. Please look into our papers for those approaches. Here is the results we got using from Funkry. Note that Funkry cannot directly comparable with Ghidra or HydraHex Pro because Funkry is trained to find those functions which are missed by Ghidra. So we combined our Funkry with Ghidra and compare with the state-of-the-art tools, Ghidra and Hexray, for this inline function recovery task. And we achieved state-of-the-art performance for all the 5 optimization level. And also, together with Ghidra, Funkry recover most unique functions. So let me summarize the contribution of this paper. In this paper, we propose an approach to build C-based project on large scale. We also showed that the pre-trained models are beneficial for inline function recovery tasks. So for Funkry, we use Roberta-based model, which was trained on 1 billion decompiled source code, and we then fine-tune it on our prepared dataset. And at the end, we also showed combined with Ghidra, our model Funkry can outperform Ghidra itself and Hexray on library function recovery tasks. So thank you.
Thank you, Tawfiq. So just on time, that's fantastic.
Thank you.
We have Saket, who will be presenting Inspect.js, leveraging code similarity and user feedback for effective taint specification inference for JavaScript.
Can you see my screen?
I can.
Okay, let me start. Hi everyone, I am Saikat. I'm a PhD student at UIUC. So today I'll be presenting our paper, Inspect.js, which is an approach for leveraging code similarity and user feedback for effective taint specification inference for JavaScript. This is a joint work with Diego from UBA, Shuvendu from MSR, and Max from GitHub. It is well known that web applications are plagued by potential security risks. Some examples include attacks like NoSQL injection and cross-site scripting. JavaScript is the most popular language that is used to build web applications. Hence, if we can develop techniques to ensure JavaScript programs are free of such vulnerabilities, then we can also make web applications safer. Taint analysis is a branch of data flow analysis that can be used to detect such security vulnerabilities in programs by detecting flows between untrusted and sensitive program points. However, taint analysis in most cases also requires some specification, which are known as taint specifications, to indicate what are those untrusted or sensitive program points that we need to analyze. Taint analysis can be used to detect violations to various security policies. Some examples include integrity policies that forbid flow from untrusted sources to sensitive things, such as making database queries, and confidentiality policies that forbid flows from sensitive sources to untrusted things, like entering a password. However, to check these policies, we need to specify what are these sources or sinks or sanitizer APIs that are used in the code. Sanitizers are functions that prevent unsecure data flows between a source and a sink. Developers often do this task manually, for instance, by using the API documentation that comes with the library. But as you can imagine, this is labor intensive and may lead to incorrect or incomplete labeling. Our goal in this work is to answer this question. How do we automatically import taint specifications that are currently missing that can complement the manual models the developers use? The input specifications can then be integrated into a static analysis framework like CodeQL to improve the manual models. To address these challenges, we developed Inspect.js. Inspect.js is a machine learning-based approach for inferring taint specifications for JavaScript libraries that can complement manually modeled specifications. At a high level, it takes some seed taint specifications and a set of training projects as input, and then it learns a set of new specifications and uses them to detect program elements in the test projects. Inspect.js also incorporates developer feedback to further refine the predictions. In this work, we focused only on inferring sinks, since they are often library specific. Sources are often shared between libraries, hence we do not predict those. And unknown functions are already considered sanitizers by default in the CodeQL framework. Hence, we also do not consider sanitizers in this work. There are three key phases in Inspect.js. Our first component, Selden star, frames the problem of learning API roles from its usages in the training projects as an optimization task. Then it uses the learned specifications to infer new sinks in the test projects. In the second step, we use code similarity-based refinement step to further filter out false positives and improve the precision of prediction. In the third step, we leverage user feedback to further refine the predictions and allow developers to quickly triage through all the predictions that Inspect.js gives them. The info taint specifications can be easily combined with manual taint specifications in a static analysis framework like CodeQL to boost the taint analysis and improve the vulnerability detection. Let me now quickly summarize the results that we had in the paper. So we used Inspect.js to predict sinks in libraries from three popular CodeQL security queries: NoSQL injection, XSS, and tainted path. Using Inspect.js, we were able to find new sinks in all three queries. And using our predictions, we sent 3 pull requests to CodeQL developers to augment the existing models with new sinks. However, we also observed that the raw predictions had low precision and required a lot of triaging. Hence, our code similarity-based refinement step also helped in this regard. It helped reduce triaging effort by 1/3. In the future, we are also working on expanding Inspect.js to new security queries, inferring source specifications along with the sinks, and also developing specialized embeddings for further refining the predictions. So with that, that brings me to the end of my talk, and I'll be happy to answer any questions later on. Thank you.
Thank you, and an award for finishing early. That's great. Okay, next up we've got Yoon Peng. Excellent, I see you. Who will be presenting Static Inference Meets Deep Learning, a hybrid type inference approach for Python.
Yes. Okay, can you see my screen?
We can.
Okay, So hello everyone, my name is Yun Peng and I'm a PhD student from the Chinese University of Hong Kong. And I'm going to present our paper named Study Inference Meets Deep Learning, a hybrid type inference approach for Python. So Python type inference is a well-explored task in the past few years, and generally we can classify the approaches into two major categories. The first category is static inference techniques, where the parity checker is a representative. Static inference techniques are accurate, and some of them can even be proven sound, but they usually suffer from the coverage problems as they cannot infer all the variables in the code. The second category is the deep learning models. They are feature agnostic and free from the coverage problems. They are also very effective on some common types. However, they provide no guaranteeing for the correctness of predictions, and they can never predict unseen types in the dataset. So as the static inference and deep learning models both have unavoidable problems, our basic insight is that can we leverage both techniques to build an approach that have higher coverage while not sacrificing the precision? So based on this insight, we propose HiTyper, and this slide shows an overview of it. To bridge the communication between the static inference and neural prediction, we first propose a novel graph representation named type dependency graph. The type dependency graph maintains the type dependencies between variables and have some empty nodes for HiTyper to fill the types. Thus, we can reformulate the type inference task into a blank filling problem based on it. So after generating a blank type dependency graph from the source code, HiTyper then passes into the static inference part to infer types. The static inference part has two major components. The forward type inference aims to infer types, and the backward type rejection aims to filter out the wrong predictions from the deep learning models. So if the static inference part itself is able to handle all the variables in the code, then we can get a fully inferred type dependency graph. And under such case, HiTyper will directly output the result. But in most cases, we can only get a partially inferred type dependency graph, so that we need the deep learning models to predict. Under this way, HiTyper will select some key blanks in it and pass them to the deep learning models for prediction. As HiTyper is independent of the deep learning models, so here we do not introduce the details about them. After HiTyper gets the predictions from the deep learning models, it then uses a similarity-based type correction phase to alleviate the issue that deep learning models cannot predict unseen types, and then it passes the predictions back to the static inference parts. Static inference parts will then infer the rest variables and reject the wrong predictions. The interactions between the static inference and neural predictions may happen several times until HiTyper gets a fully inferred type dependency graph. And in these slides, we show an example of such a type dependency graph. And generally, there are four kinds of nodes in it. The symbol nodes that indicate the variables we need to infer the types. The expression nodes that indicate the expressions generating new types. And branch and merge nodes that handles the data flow. The most important part of HiTyper is the expression nodes. We design expression nodes for every expression defined in the Python's language specification. And for each expression, we design the corresponding rules to infer and reject types. Our rule has the base format in the right, which means that the expression E has the type delta under the context pi. We also list an example of rule here. In this rule, the first part of conclusion indicates how we can calculate the result type for the expression, and we call them typing rules. The second part indicates how we can validate operand types, and we call them type rejection rules. The forward type inference process and the backward type rejection process are conducted based on these rules. As we can store the rules in the expression nodes, then we can reformulate the static inference process into a graph traversal process. For the neural type prediction, we add two parts to further reduce the wrong types predicted by the deep learning models. The first is a hot type slot finder, in which HiTyper only passes the important variables for deep learning models to predict. The second is a similarity-based type correction, in which HiTyper maps the never imported type predictions into a valid type. And this slide shows the performance of our tool. as we can see that HiType shows an 11 to 50% of improvement on the overall type inference. And the most significant improvement is on the return value inference, which is about 20 to 40%. So the above is a brief introduction about our paper. To better know our work, you can access the resources listed on this slide. Thank you.
Thank you, Yoon. All right. And our next presenter, Mohammed Wardat, presenting deep diagnosis, automatically diagnosing faults and recommending actionable fixes in deep learning programs.
Can you see my screen?
We can.
Hello, everyone. I am Mohammed Wardat, a PhD candidate at Iowa State University. I am going to talk about my paper, Deep Diagnosis, our paper. This is a collaborative work with my advisor, Dr. Adesh Rajan, Dr. Willie, and Dr. Bruno Dantes Cruz. Deep learning is being used in several safety critical applications because of that bugs can have a big impact on the user lives. Thus, testing and verifying systems that use deep learning is very critical. In this work, we aim to improve the reliability of deep learning application by diagnosing bugs and provide fix suggestions. A developer working on the following code. The code is for a sequential. Unfortunately, the code is having low performance during the training, and the developer don't know how to solve the problem. Because of that, the developer decide to use Stack Overflow to ask the following two questions. Why do I get a bad result for simple data set? Is my data set malformed? As a researcher, I try to help the developer and run the state of the art on the code. The results are as follow. When using Omelette, the training was terminated and without identify any bugs. When using Deep Localized, the training was terminated and it indicated that there is a numerical problem on layer 7. When using Auto Trainer, the training was terminated and it is not able to fix the problem. Unfortunately, none of this technique can answer the developer's question and indicate how to fix the bug, thus indicating that additional research is needed in this area. Existing technique propose different analysis method to detect bugs in the deep neural network, but they don't correlate the symptom and the root causes. They don't detect bug that manifest the trend of value and don't offer possible fix. To fill this gap, we propose deep diagnosis, an approach that maps symptom back to their root. To that end, this work make three contributions: study different type of symptom and propose dynamic analysis approach for detecting and provide possible solution to fix. An evaluation on a 444 big model from real life and prior work, demonstrating the effectiveness of the approach compared to prior work. The result shows that our prototype is more effective and efficient than prior work. This figure provides an overview of our approach, which contains three parts. The left part, the approach started by running initial model and passing our callback. Middle part, this callback allows capturing and recording the key values such as weight and the gradient during feed-forward and back propagation state. A dynamic detector is applied to report different symptoms such as dead node saturated activation function at different stage based on the error condition we define. Right part, when a symptom is detected, the approach will analyze the recorded key value and determine where the best location in the original model to fix the problem. We propose a decision tree to map a symptom to fix. The main goal of the decision tree is to mitigate the manual effort and reduce the time for diagnosing and fixing the bug by mapping the path from the root to one of the leaves. The decision tree here consists of 24 rules which map a symptom into one of the 7 classes of the changes. In this work, we aim to answer the following research question. We cover research question 1 and 2 in this talk, and for research question 3 and 4, please see our paper. Research question 1, can our technique localize faults and report their symptom in the deep learning programs effectively? Research question 2, how effectively and how fast can our technique localize fault and report the symptom compared to existing methodologies? To answer research question 1, we compare deep diagnosis with AutoTrainer, deep localized, and omelette. Our result shows that deep diagnosis can successfully detect different type of symptom and report actionable change. It outperform these tools. To answer research question 2, we evaluate the efficiency of deep diagnosis in the term of the performance. We measure the analysis time for deep diagnosis and other state-of-the-art tool for source of the benchmark, Stack Overflow, GitHub, and the Scopus paper and AutoTrainer benchmark. From the figure, deep diagnosis has lowest runtime in Stack Overflow and the Scopus model, but it has higher runtime compared to Omelette and on the GitHub model. Deep diagnosis is faster than AutoTrainer on all benchmark except for the blob and circle dataset. In conclusion, we propose a dynamic analysis approach to detect error and receive useful message for DNN bugs. Our result shows that deep diagnosis outperform the state-of-the-art tools. More description can be found in our paper. Thanks a lot for attending the presentation.
And thank you, Mohammed. All right, our last and final presenter today will present striking a balance, pruning false positives from static call graphs.
Hi, I hope you can see my screen.
We can.
Okay, that's great. Hi, my name is Akshay, and I'm a PhD candidate at UCLA. And the topic of the presentation is striking a balance, pruning false positives from static call graphs. So here's an oversimplified view of how a static pipeline might work. We have a program that's fed to a call graph construction tool. And this call graph construction tool itself is a kind of static analysis. And its output is a call graph. So a call graph is a graph of all the method calls in a program. And a client analysis, like a null pointer analysis tool, builds on top of this call graph to produce null pointer warnings. So we define two terms here to quantify how well a static analysis is doing. So precision is defined as out of the static analysis, warnings or edges, how many were true positives. And you can think of precision as 1 minus the false positive rate. The second term, recall, is defined as out of the ground truth errors, how many did the static analysis catch? And the precision and recall of the call graph directly affects the precision and recall of the client analysis because it's built on top of this call graph. So let's look at one issue with current tools. So user studies conclude that static analysis tools should aim for 80% precision, but current call graph construction tools like Wala, among others, have a call graph precision of 24% and a recall of 95%. Here we're assuming that the dynamic analysis gives the ground truth. So why is Wala designed this way? And the simple answer is that it's a recall-focused verification tool, which is fine, but there's definitely a gap between what Wala can provide and what users expect. So here is our solution to this problem. We start off with a program as usual, which is given to a call graph construction tool that produces a call graph with 24% precision and 95% recall. And we feed this call graph to a new unit called a call graph pruner. So the call graph pruner is going to prune away mostly false positive edges and a few true positive edges, thereby giving us a call graph with 66% precision and 66% recall. So let's go a little deeper into the solution. So our solution can be broken down into two components. The first is a classifier generator. So this is an automatic ahead of time learning process to generate a classifier. So the classifier generator can be thought of as a function that takes in 3 inputs: a static call graph constructor, a dynamic call graph constructor, and a set of training programs, and it outputs a classifier. So this classifier is going to be used in the second component, which is the call graph pruner. And we can think of the call graph pruner as, again, as a function that has three inputs: an existing call graph, a learned classifier, and a threshold, and it outputs a pruned call graph. So the threshold here is a parameter set by the user to decide how aggressively the call graph pruner will prune edges. So we saw that the call graph pruner can improve Wala's call graph precision from 24% to 66%, but we're also interested in what effect this has on a client analysis. And we use a null pointer analysis as an example. So with the original call graph, the null pointer analysis had 27% precision. So you can imagine how a user seeing 3 out of 4 errors being false positives is frustrated with using the tool and ignores its output. But with a pruned call graph, we may report fewer errors, but we get 77% precision. So at this point, most of the errors are true positives. And that's it for the talk. Thank you for listening.
Thank you, Akshay. So, welcome again, everybody. Hopefully you're here for most of the session or just a paper you wanted to see. And now is our chance to open things up for discussion. Anybody who has a question, please feel free to raise your hand, and I will try to sort through the hands. Okay, do I not see the hands? Or is everybody thinking deeply about that first question? Well, let's see. I can start us off with a question. Oh, wait, do we have a question?
Yeah, I actually had a question for Saikat. So
Please.
Oh, I see. I just saw that.
yeah. So
Okay,
my question
answer
more
that.
generally is, how does this work compared with like previous work on specification inference?
Yeah, so Merlin was one of the earliest works in specification inference. So there, what they used is they just used probabilistic inference. So basically, they construct all these rules from the data flow graph, and then they use basically Bayesian inference to infer the sinks, the sources and sanitizers. So Selden was another recent work, which is an improvement on that. Which uses a more approximate method. Basically, what they do is they create this an optimization task, right? So basically, they all have these basically approximate rules created from the data flow graph, and then they basically solve it using some kind of a solver. In their case, they use the PyTorch optimizer, right? So our work is also based on Selden. So we also make some improvements, some optimizations on Selden's core approach to basically make it more scalable. So Selden's basically main contribution was to make it work for Python. In our case, we focused on JavaScript. But when we directly applied Selden's approach to JavaScript programs, it simply did not work. And also, there were a lot of problems with scalability. So in this work, we focused on how do we improve the scalability of inference. And we also involved various kinds of optimizations for data flow when creating data flow graphs and then creating constraints from those. But apart from that, in this work, what we focused on is how does a developer quickly triage through all the predictions? Because whatever predictions all these tools give you, they may contain a lot of false positives, right? So we had two steps. So one is just based on code similarity. So we use contextual similarity to basically separate true positive things and false positive ones, right? So that is based on code similarity. And then we also have a feedback leveraging steps where we allow developers to also give feedback in what they think are true positives and false positives. And then we also refine predictions based on that. So these two steps on refining the predictions are the main contributions, plus the optimizations that we made on Selden. I hope that that answers your question.
We also have a question in the chat for Akshay.
Right, I see the question. The question is, can you elaborate on how the static and dynamic call graphs are combined to remove likely incorrect static call targets? Right. So, so our approach has two phases. We had the call graph. We had the classifier generator, which is sort of a training phase in which we provided a large number of static and dynamic call graphs and learn a classifier that learn a classifier over a certain feature set, which will learn to the classifier will learn to predict which edges are likely false positives. And then at test time, that is when we're running on a previously unseen program, we use this classifier to make a prediction about how about whether or not it's true or false positives. So the high level idea is we just cast the problem as a machine learning classification problem with the dynamic analysis providing the labels, and then we use an off-the-shelf machine learning library. I hope that answers the question.
Yes, it does. Anyway, we can follow up. I want to leave time for other questions. Thank you.
And Akshay, can I ask you a quick question? So often there's a trade-off between precision and recall. And, we can create high precision sometimes by focusing on the clearest signal. Can you give us a sense of the magnitude on your slide? I think you showed there's about 70% precision. How many data points would a developer be looking at that point?
I'm sorry, I didn't get the last part about the data points.
Yeah, how many examples? So in terms of 77% precision, how many examples would they be looking at where they might have to filter through false positives? Would it be 5 total, or? Oh,
So
you're muted.
You can think of precision as the inverse of the false positive rate. So if precision is 70%, they could expect around a 30% false positive rate. And as to how much you want to trade off recall for precision, that can be a little user dependent or application dependent. So different applications have different preferred trade-offs between recall and precision. I'm sorry, did that answer the question, or did I misunderstand it?
Close. So I normally think of precision recall in terms of information retrieval. So there's some number of results. So are we talking about a large number of results, a small number of results?
Yeah, we're talking about a large number of results.
Okay, thank you. That was my only question. I'm sure the answer's in the paper too. We have another question for Mohammed from Psycha. Can you elaborate on what kind of bugs cannot deep diagnosis handle? Also, what is the precision of the fixes proposed by your tool?
Okay, for the bugs, our tool is focusing on the hyperparameter related to the neural network, the DNN, and it is not support right now any hyperparameter related for convolution neural network or LSTML model. And there is for the percentage for the accuracy, our tool is able to detect 46 out of 53 model that this model selected from Stack Overflow and GitHub and the prior work. And for the correct precision, correct for provide suggestion, there can be able to provide suggestion 28 out of 53. I hope I answered the question.
Yeah, and I have a follow-up there as well. So I saw MNIST was included. Which MNIST data set is that? That's not the handwriting data set, is it?
Evaluate the model. Here is the model that used to evaluate is not just like MNIST models. is we collected this model from Stack Overflow and GitHub, and this model have two types: binary classification and categorical classification and regression. It's not just related for any stuff.
Okay, interesting. Thank you. All right. Any other questions here? I know we have a lot of people in the audience. This is your chance. Get the answer from the authors directly. And I don't see any hands. So if you're raising your hand, just unmute and ask your question.
Yeah, actually, my question is for Mohammed, and it's sort of an extension of Saikat's question, which is, so are there any bugs which are more prevalent for deep neural networks as compared to regular programs? And what is it that makes yeah, so that's my question. Actually, it's an extension. Like, what kind of bugs would you see for DNN programs that we don't see for usual programs?
Yeah, first, our approach is focus on the structure bugs that is make the low performance for the model. For example, if you select any hyperparameter wrong, for example, use last layer, for example, sigmoid instead of softmax, this will be effect on the performance of the model. Our tool is able to detect these kind of the bugs and try to provide some suggestion by a change activation function, or if the data is not normalized, give you a hint like to normalize the data.
And in this context, a bug is it's a significant loss of performance that you're detecting. Is that correct?
Exactly, low performance for them
Okay, that's quite interesting. Let's see. I did have a question for Tawfiq. I think you've largely survived unscathed. I can't say that my question is going to be difficult, but one thing I was interested in was, and this is somewhat related to one of the chat questions, what about the limitations? So, you've created this large data set, and I think along the list that there are some hard problems, right, still waiting to be tackled. Do you have any thoughts or insights that you could grant us from your experience there?
Yeah, so most of the work we did in this paper was we worked with unstripped data. So there are some papers also that deals with like stripped data set, like after stripping the binaries, how this decompilation will do. And we have seen that after stripping, all the identifiers are gone. It's very difficult to reverse engineer this binary. So this is one prospect, like we are actually aiming to look in future, like how can we process more efficiently these stripped binaries. And also in our TC paper, we mostly look into the inline function recovery. But we are also interested about how can we retrieve the original source function for the given decompiled code. So if the decompiled code is given, if you can generate the actual source code for the reverse engineer, that would be great. So these are the possible research direction we are currently looking into, and this is a very challenging problem. When you look into the strip binaries, even the machine learning, high capacity deep learning model faces a lot of issues. And there are several works which try to address this the typing problem, like finding the types in the decompiled code, because the types are also gone. And some of them are trying to there are several works that are going on, I think, in this area, and we are also trying something. But with strip binaries, it's very difficult compared to unstripped one.
Nice, thank you. And it sounds like you're in an actively researched area with people looking for different artifacts. Maybe some of those approaches will be beneficial to you.
Yes, thank you.
Yun, how about you? Is there, for example, a limitation that you discovered along the way that in the space of type inference that you feel is part of your future work? Or maybe for others?
Yes, actually, our framework limitation is that since our framework use the static analysis framework to validate the predictions from the deep learning models. However, in the whole workflow that indeed the deep learning model does not learn some new things from the static knowledge, they still do not know what kind of prediction is correct or is incorrect. So in my next step, I will consider to fusion the static knowledge into the deep learning models. For example, we can use some kind of reinforcement learning techniques, such as we let the static framework becomes environment, and then we can let the deep learning models to explore what kind of predictions is statically correct. And then I think the deep learning models may learn more some kind of the type correctness and generate more accurate type predictions.
All right. And let's see. Akshay, I don't think, did we ask you about your insight into future work that you discovered from this work?
Right. Future work would so in our work, the feature set was actually hand designed. So one future work would be if the feature set could automatically be learned from data, which is a pretty hard problem, but one definitely worth looking into. A second thing is we obtained our labels using dynamic analysis, which is really scalable, but sometimes we'd actually care more about a developer labeling the errors as true and false positives, or edges in the call graphs as true and false positives by hand. But an interesting problem would be how you can scale this up to a very large number of errors and then use that as the ground truth instead of the dynamic analysis.
Thank you. And let's see, Mohammed.
Yes, for our paper, we are planning to support different type of bugs, some bug related for the convolution neural network or LSTML model, like LSTML model. Also, now our tool just provide a hint for the developer how to fix the bugs. We are trying to make this as automatically for repairing the model without developer intervention.
Oh, I'm sorry. I think I hid Akshay. I apologize, Akshay. Maybe our student will help us get you back. Thank you, Mohammed. Apologies. And Saikat, are there future directions or problems, challenges that you've discovered through this work?
Yeah, I guess the main challenge for us is the precision, right? So right now, the precision of the tool is quite low. There are many false positives. I guess in our work, we focus more on high recall. So that is why we had too many false positives. However, the two-step refinement process using code similarity actually helped cut down triaging time. So in the future, I think one direction is, so in this work for code similarity, we used GraphCodeBird. So we use the pre-trained model to figure out the contextual similarity between predicted and known things. I guess in the future, it will be great if we can figure out a way to basically fine-tune or basically develop some new models to do better refinement, right, and improve the precision of the predictions. So that is one thing. And secondly, I mean, that is the easier part, is just expanding our approach to other security queries. So in this paper, we just focused on 3 XSS NoSQL injection and tainted path. So just expanding it to other kinds of security queries in CodeQL, and also expanding to sources, inferring source specifications. So those are some of the few things that we are looking at.
That's great. And then, there was this question earlier about scaling up user input, user feedback. You're working with user feedback in your approach.
Yeah.
You also face that scalability challenge?
Yeah, so that is where the code similarity actually helps. So for each prediction that we give to developers, we actually created a UI where if the developers have 2 options, whether to accept or reject every prediction. And if they reject the prediction, they also have another option to reject similar predictions. So there we again use the code similarity based refinement step to hide other predictions which are also similar to the ones developer thinks is a false positive. So that helped cut down the triaging effort. But again, if we later on develop some custom embeddings or custom models that can further help to speed this up. So in our work, this helped cut down the triaging effort by 1/3, as I mentioned. And I guess with better models, this can only get better.
Interesting. So maybe the lesson learned there is if you can find a similarity metric based on some feature of interest, you can use that to batch potential false positives that you can trim out. Lucky, there was a question, Akshay, that you had for UPenn. Oh no, did we lose you again?
Yes. So the question I had was that you said that you used a static type checker to verify if the types that you had given are correct. And so my question was, suppose you had an identity function, and let's say your tool predicted that the type of that function is that it takes in an integer and gives out an integer. And the static type checker will say that this is valid, but the int arrow int may not be the sort of the correct or the best type for the identity function because it's much more general than that. So what would your tool do about that?
Yes, I understand. Things in some cases that the static constraints cannot limit the valid type set into a single type, and actually there can be multiple types that are all valid in a single function. So under this case, that's why the deep learning models is involved, as the deep learning models can take a lot of high-level type hints, such as the identifier or some kind of the variable names that the developers may use such information to indicate what kind of type it may be. For example, if we name a variable text, then it is more likely to have the type string, even though that the static type checker thinks that the integer or a floating number is also valid. So I think the deep learning models can help the static checker to choose the most likely type in the type inference task. So this is why actually the deep learning models are very effective on this task.
Got it. I had a small follow-up question, which is, in this case, how do you verify correctness?
Well, the correctness here, we define that if you do not violate any kind of typing rules inside this code, then your type prediction is valid. So if there is no operation or expression in the code that indicates that the variable text cannot have the type integer, then actually integer can be a valid type. So although that under some cases you may have some external functions or some external context that limit the type into a single one, but we do not consider that specific context as we are considering the general context.
All right, we probably have time for one more question, maybe two. Anybody having that Last burning question. Not seeing anything. Going once. Going twice. Someone's always going to ask the question right after we thank the speakers, right? All right, I thought that would tease out that last question. I don't see it coming. Well, we've got 5 minutes left for the session. Let's go ahead and thank all of the speakers. I thank you all. You did a great job presenting your papers in 5 minutes, which is a Herculean task for anybody. And I know there's a lot of unanswered questions for all of us, and papers are available for those deeper dives. If anyone wants to hang on, I'll stick around for another 5 minutes. You can just jump in and say what you want to say. Otherwise, this could also be a chance for you to grab a quick break before the next session. Okay. Thanks, everybody.
Thank you very much.
I think everybody's headed off and want to take advantage of that break.
Yep. There's some noise on your end, I think.
Yeah, there's I apologize about that. Midspace needs extra computing power, so it spins up my fan. I'll try to use as much as possible. Is it pretty bad?
Yeah.
That's awful. Okay. Let me try this. Maybe we're going to bump this for my next session.
Yeah, there's a lot of background noise from everyone.
Oh, okay. Is it still for me as well?
Yeah, so
Yeah.
whoever speaks, there's always some background noise. But it's only been happening the last couple minutes.
That's interesting. That's too bad. Yeah, when I Zoom, somebody will apologize because somebody's mowing the lawn or something outside, and I can't hear them all. So Zoom sounds really noise canceling.
Are you traveling to the in-person event, Travis?
I live in Pittsburgh, so I was not having to travel far. But my family has scheduled a vacation. so I kind of have to go. But yeah, unfortunately, I miss my experience in Pittsburgh. That's great. Are you going?
Yeah.
Excellent. If you need restaurant recommendation, there's some amazing. It's a small town, but not too small.
Yeah, I've been there once before.
Yeah.
It was in PLDI 18.
Okay.
Hi, Psychic. We met here. Hi, Psychic. Do you remember me?
When did we meet?
We met at Illinois software seminar. I'm an intern student of Darko.
Oh, I see. Did we actually meet in person?
No. Virtually,
No, right?
Always virtually.
Oh, virtually. Yeah. Okay. Well, I can't remember face.
Do you plan to attend the in-person conference?
Yeah. I'll be there.
Oh, okay. Then we will meet at Pittsburgh. Very cool.
Yep. Cool. Yeah, this time in person. So I'll remember your face.
Exactly. Without the physical interaction part of forming memory.
Yeah.
Well, I'm gonna head off. It was really great meeting all of you, and enjoy the physical conference. See you later.
Hi, Travis. It seems that there is some noise in